Hi guys, today we will be discussing about the escape velocity. The escape velocity is the minimum velocity required to escape from the gravity of a planet. This planet could be the Earth, the Mars, the Moon or any other particular planet within the solar system we are in or any other solar system. This means a particular particle or particular object won't reach back to that particular planet after it is being shot out. If we shoot an object with a minimum velocity required to escape that particular planet from the gravity, we say that that's the escape velocity. So there won't be any energy added along the pathway. Consider a rocket. If we consider a rocket, we assume this to be obeying the escape velocity. But this is not a principle of escape velocity because the rocket would have a particular energy stored within it as well. So this particular rocket can move or escape the planet Earth with adding speed with the fuel it possesses. With the combustion of the fuel, the rocket would increase its velocity or the speed and leave the planet Earth. From the conservation of energy, we know that the initial energy is equal to the final energy. So we apply the same principle here where E is equal to E dash. E is the initial energy whereas E dash is the final energy. So in this situation, we know it's influenced by the kinetic energy and the potential energy. The kinetic energy of the particular object we take as half m naught E naught squared minus the potential energy, we know that this is G times m naught times m. Here we consider the Earth situation, so me over Re, where Re is the radius of the Earth. This is equal to half m times or m naught times of the mass of the particular object E naught dash squared plus G times m naught over R infinite times the mass mg. So here we know that this particle or the particular object would have a velocity which is equal to 0 at infinity. And since R infinity is an infinite system, we can see that this particular term divided by infinity would go to 0. So we can see that this particular equation is simplified further. The energy term which remains is only the kinetic energy and the potential energy of the initial situation where the object was on Earth. So half m times m naught times V naught squared minus G times capital M E times m naught divided by Re, where R is the radius of the Earth, is equal to 0. So we can simplify this further and say that this m naught will be cancelled off and the equation which remains would be V naught squared is equal to 2 times E times m times E divided by Re. So This particular v naught is the velocity required by the particular object to escape the planet Earth in this particular situation. So the velocity or the escape velocity v escape is equal to 2 times g times m times me over re square root. So this is the escape velocity of the particular object. So we can see that the escape velocity only depends on the constant g and the radius of the earth re and the mass of the earth me. So here we can see that the mass of the object won't be considered here. So any object, it could be a small, a large object. If we attain the escape velocity for Earth, we can see that it won't have any effect. We can also use another simplification. The escape velocity for the situation is also, we can assume to be as a work done. So the work done to bring a mass or object from a planet to infinity. So this is also another simplification we can do for this equation. So we know that the work done W is equal to the integration of Re, where the Re is the radius of the planet, to infinity f dr. This is equal to Re infinity g m over r squared dr. So now we can see that this particular equation is also further simplified. So this is equal to minus g times m divided by simple r or rather capital R in between Re and infinity. Now the solution we obtained through this is the work done. So this work done is equal to the kinetic energy this particular object possesses to escape the planet Earth. So this is the escape velocity. So we can simplify this down further into the escape velocity. The escape is equal to 2 times g times m divided by Re the square root. So in both the calculations, the escape velocity we obtained was 2 times g times m divided by Re the square root of it. So as we can see, the mass of the object is not come into a consideration. So this is about the escape velocity situation. Thank you for listening.